Today I want to do a very quick introduction on what does a compiler do, and I want to do that introduction using a bit of a different approach. Usually people just talk through it, show some diagrams. I want to actually go through all of the source code in a very simple compiler that's just 300 lines of code. Um, and as I go through it, I'm going to be doing a very high-level explanation of what that code is doing. This is the main file of a compiler. A compiler translates some high-level language into machine code. So the first thing that it does is it defines a source variable from this file here. So if I open that file, examples factorial, that's a file, and I'm just going to read that file and convert that to a tree containing all of those expressions, and that's going to be my source. Then I'm going to call this source to assembly function, and that generates a bunch of instructions in the desired architecture. In our case, that's AMD64. And then we run that through the optimizer, which is just going to locally try to eliminate redundancy and things, convert instructions that are slow into instructions that are fast, etc., etc. And then once we have this optimized bunch of instructions, we just convert that into a program. Converting instructions to a program means actually generating the machine code from those instructions. So that's another name for an assembler. Um, and then we have this program to file function, which takes in this machine code and writes it to a file. There are some complexity there because computers don't actually execute just the plain machine code because they have operating systems, and the operating system has to know how to load those instructions into memory and then start executing them. So for that, we have specific types of files. In this case, the ELF file, which most Linux architectures and distributions use. Um, and we are just going to write that machine code wrapped into a ELF file. Okay, so let's quickly check what this source to assembly function does. It's defining the compiler file. So let's check what it does. Source to assembly, it iterates through the source and then generates code for each expression in the source. So if I open our factorial file again, which is the source file, this is going to be the first expression, second expression, third, and fourth. And it's just going to generate code for each one of those. How does it generate code? It just checks what kind of expression that is, and then generates code for that specific expression, calling emit expression recursively for other things. For example, if you have defined something and that thing has some body, like for example, you're defining a function and then you have the body of the function, you can just call expression again to evaluate and generate code for each one of the things that's happening inside the function. In terms of what is it actually generating, it's just generating these instructions in the following format. So an instruction is just a list of things. The first thing is what kind of instruction it is, and everything else is just like arguments to that instruction. And there's a very handy website for AMD64, which is called the AMD64 reference essentially, and it's by this guy here. So, and you can just use that to check like all the instructions that you can execute in AMD64 CPU. So you can just go over those and check like what instructions you need. But for example, let's check some of the instructions that we're generating here. Let's check something interesting. So for example, to generate a if statement, right? So we call emit expression on the expression that we want to check if it's 0 or 1, or in this case like true or false. And then we just use this CMP instruction to compare the values of that expression and 0. So we are comparing the expression against 0. So you can see here we have ASM load into register 1, the value is 0. And then we compare the register 0, which has the value of the expression, with the register 1, which has 0. And then depending on the result from that comparison, we either jump into the else label, or we continue straight ahead, which executes the if body, and then jumps to the end of the function. If we jump into the else label, we execute, which is here, we execute the code for the else body, and then we are done. So that's a simple example of how you generate the actual assembly instructions. Cool. So we have this source to assembly function, which given some source tree, it generates this sequence of instructions. Cool. What's the next thing that we do? We call the optimizer. So let's check what does the optimizer do. So that's the optimizer. It just runs a bunch of times optimizer 4 on top of that list of instructions. And then from that result, it runs optimizer 2 on the resulting list of instructions. And then it calls itself again for this number of times that we specify here. So 8 here is arbitrary, no exact reason for choosing 8, but the idea is essentially that there are some optimizations that you can execute after executing other optimizations. So if you execute the thing a bunch of times, it's essentially going to optimize to the maximum possible extent. The proper way of doing it would be, instead of like doing a fixed number of times, for example, you could check if optimizing further is not changing the instructions, and that means that you cannot optimize further, or you could do something else smart. But we are just doing the dumb thing here, and the dumb thing is for optimizer 4, we take the first 4 instructions in the list of instructions, and we check if they follow a specific pattern. In this case, push something else, pop something else. And that means that we push something to the stack, push something else to the stack, and then pop those two things right afterwards. So if we are just like pushing and popping things, there is no reason to push into the stack. We can just move things directly from one place to another. So we can just move, for example, A into Y and B into X. And that's what it's doing. It's exchanging those 4 instructions with just like 2 mob instructions. And the good thing is mob instructions don't even need to go into memory, while push instructions do need to go into memory. So that's much faster. And then we have a bunch of other similar optimizations, and some of them you can see they check if some of the instructions are not stack or control flow related, because they do not fit into the model that we are trying to reduce here. Okay, and then we have similar thing for optimizer 2, but instead of like taking 4 instructions, we take 2 instructions. And a very simple example of that is similar to the one that I showed for 4, but we just push something into a stack and pop something into the stack and into the same variable, in the same register. So in that case, you're not doing anything. We can just drop those 2 instructions. Cool, so that's what the optimizer is doing. It's just like checking for specific patterns of instructions and generating better patterns of instructions. Cool. And then we have assembly to program. If you remember, that's the one that's going to take some list of instructions and it's going to generate machine code. If we go to the definition of assembly to program, it's in the assembler file, and it does all of those things in sequence. One thing that you can see straight away is that some of those things that we're defining here have a slash first, and other ones have a slash second. And the reason for that is that a assembler needs two passes in most cases. Because, for example, if you want to call some function, you first have to know where does that function, where is that function defined in your source code. So that means that first you need to know the positions of everything in the program, and then you can go and actually generate the code for the whole program. So the first pass is sort of doing a fake pass. It's generating the whole code, but it's generating incorrect code. And the reason is what I said before, it doesn't know where to jump. When you say jump to something, it doesn't know where something is. So it just puts 0 in there. And that's interesting because that means that the generated binary code is going to have the same size as the correct code. So you can, from that binary code, you can know the correct destinations. And then you use that in the second pass to actually replace those zeros with the correct positions. There's another way of doing it, which is just generating things on the fly and saving like the positions that you know are incorrect. And then when you find the correct positions, you just say go back and replace in that location with the new correct position. But yeah, so we are doing the first pass. We then, from the first pass, we generate a bunch of labels, and we use those labels in the second pass to generate the correct instructions. Then we just join together the machine code from all of the instructions into the program. So very simple, but it uses another file called ASM, which is the one that actually generates the binary codes for each one of the instructions. And it does that in a very simple way. You can see like the file is 50 lines of code, and it provides all of those functions that the assembler uses to generate the binary code. And the way that it does it so concisely is by checking like the general patterns of instructions. For example, there is this byte which happens very frequently, which takes in 3 arguments and generates something slightly different depending on those. And then there is like all of those different formats of instructions that we have here. And then most instructions are just like direct applications of those formats of instructions with some specific byte saying this is such and such and such instruction. And to find like the actual magic numbers used here, all of those hexadecimal constants, you can go to the reference and it's just going to say those are the numbers that you need to use to execute this instruction. And that reference, you can use that website that I showed, but also like the programming manuals for the CPUs. That's the thing that they are describing. And in here, I also created some Linux specific things. For example, ASM exit called syscall 60, which is exit on Linux. Cool. So that's essentially everything that we need. However, there is one last small piece, which if we go to our main file, that's the missing piece, program to file. So I have shown you how you can generate the machine code. However, how do you put that into a file that you can actually execute, right? And the way that you do that is, let's go into this thing here. It's essentially a bunch of magic bytes. and you can see here it just like has this first magic byte, and then it writes elf, and then a bunch of other values. Those are not magic values. They are describing the CPU architecture, the kind of binary that this is. This here, for example, is describing the position in which the code should start executing, and a bunch of other related things, for example, memory permissions, so you can define a part of the memory that's executable and something that's read-only, something that's write-only, for example, read-write, um, and all of the possible combinations of those permissions. And you are also specifying like this is the size of my program, this is the alignment size that I want to use. All of those things are specified here. And also, of course, the binary for the program itself. And then what we're doing is just like write to some file, replace it, and make it executable. Whatever bytes we get from this function here, which just generates like this header plus the program. So that's a compiler.